Here is A, here is B, here is C, here is D. So this is our Q. Why this is closed? You need to find a ball center at origin to enclose this Q, right? How to determine the radius of this ball? It's very easy. You simply take R to be the absolute value, the sum of the absolute value of the endpoint of the intervals. Then you can prove Q is a subset of BR. Therefore, Q is bounded, and we also know that Q is closed. Therefore, this set is sequential compact. Okay. So we now study continuous functions defined on sequential compact set. This kind of result are generalization of the value result we learned in single variable calculus about the continuous functions defined over closed interval. Okay. Now theorem. A is sequential compact, and the F is continuous. Then the image of F of F is also sequential compact. Proof, not difficult. You want to show that the image is sequential compact. So let YK be a sequence in the image. Take a sequence in the image. You want to show that the image is sequential compact. It's sufficient to show that any sequence in the image has convergent subsequence whose limit is still lying in the image. Okay, therefore we take this YK. So by the definition of image, every YK will be the image of some point in A. So there exists xk, for every k, there exists xk in A such that yk is the image of xk under our map F. So this xk is a sequence in our set A, but the set A is a sequential compact. So this xk has a convergent subsequence converging to a point in A. Okay. Since A is sequential compact, there exists A in A and the subsequence of xk denoted by xki such that xki converge to A. Now by the continuity of F, we see that yki is fxki. This will converge to a point Fa. But because the point, the limit point A is in A, so Fa is a point in the image of the set A. So now we have already proved for any sequence in FA, the image of our map, there is a subsequence YKI. YKI is a subsequence of YK, which is converged to some point in the image of FA. So by definition, the image FA is a sequential compact. Okay. So this is about vector value functions. We cannot talk about the order relation, which one is larger, x greater than y. We cannot talk about these things in higher dimensional Euclidean space. But if the coordinate of the map, if n equals 1, the map, then f is a real valued function over A, then we can talk about the bigger or small of real numbers. So we have all the structure to work with. Therefore, we have an interesting result. So for the next topic, I expect you understand upper bound. And the supplement and the maximum. I expect you already understood this concept very well during the study of single variable calculus. Okay, so this result is the theorem. If A is sequential compact, and f is a continuous real valued function, then I want to say f will attain its maximum value and the minimum value. Okay, but the most efficient way to express this is that there are B belongs to A such that FA is the increment of fx round over A, and this is sometimes denoted by, sometimes we use the more simple notation. Sometimes we prefer to use this simpler notation to save ink. Okay. Similarly, FB equal, of course, this means this is these are the same. Okay, but this notation is simpler. This one simpler. Okay, this is a very useful theorem. As we learned in single variable calculus, every continuous function over a closed interval, defined over a closed interval, has a maximum and a minimum. So here, because this increment is achieved, so this increment is in fact minimum. Similarly, the supplement is also achieved, therefore it is a maximum. So this theorem tells us that continuous real-valued function defined over sequential compact set can attain its minimum and a supplement and a maximum. Okay. Minimum and the maximum, these two kinds of functional value sometimes are called extreme value. Okay, just a concept. So we prove this theorem. The the proof of minimum and the maximum are similar. Therefore, we prove the result for minimum. Okay. So prove by definition of infimum, because definition of infimum, there exists a sequence of point xk in A such that fxk goes to the infimum. Now there is a question: if f is unbounded below, this means that the infimum is minus infinity. Okay, have a remark. If f is all possible to unbounded below. So if f is unbounded below, from below, then infimum is minus infinity. Okay, we don't know whether f is bounded below or not. Anyway, we don't care. If f is unbounded below, we still have a sequence in A, so the fxk goes to minus infinity. Okay, so this is true regardless of whether f is bounded below or not. So xk is a sequence in the set A, and A, by our assumption, A is sequential compact. Therefore, by the sequential compact of A, our sequence xk has convergent subsequence denoted by xki. So xki converge to a point A in our set A. Right? So by the continuity of f, since f is continuous, fxki will converge to fa. fxki, because f is a real valued function, fxki and fa are real numbers. So this conversion is simply the convergence of a sequence of real numbers we learned in single variable calculus. Okay, but on the other hand, this fxki is a subsequence of fxk, and we know that fxk converges to the infimum of f over the set A. So by the uniqueness of conversion, we must have fa equal the infimum of f over the set A. So this is the result we want. And from this result, we also know this also implies that f is bounded from below. Why? Because f is a real valued function.